Hello, everybody. Our new unit will be sequences and series and probability and combinatorics. It's a lot of stuff. None of it is mostly intrinsically that hard. The other blocks said that they got a little bit frightened when they saw the big E-looking symbol here, sigma. But you'll see soon that it's actually not that scary. There are a lot of really interesting ideas in this unit. A typical teaching order is to talk first about a thing called a sequence, and then about things called series. A sequence is just a list of numbers. It's an ordered sequence of numbers. A series is what you get when you have a sum. The word series just means sum. And in calculus, very frequently, you're interested in thinking about what happens for infinite sums. So what would happen to this sum if it just kept going? 1 plus a half plus a fourth plus an eighth plus a 16th. And we talked about that a couple units ago, I think. In some cases, it's a little bit less obvious. So what if I have 1 and I subtract a half and add a third and subtract a fourth and add a fifth? If we were in class, I would have you pause and discuss with the person next to you, because it's good to form an intuition about what's happening. It turns out that thinking about infinitely long sums is easier if you know how to think about sequences first. And so today we're going to start with sequences. So let's get into a couple of notes here. First, just vocabulary. Set, sequence, series. So a set is a collection of things. In our class, the things are going to be numbers. So here's a collection of numbers. 8, 6, 4, 2. And usually designate a set using curly braces here. Sets can be infinite. You could have an infinite number of numbers, so the set of all integers is a set. Sets can also contain things other than numbers. You could have sets of functions. You could have sets of other sets. But right now, think about a set as a collection of things where the order doesn't matter. So these are the same set. That set is the same as the set 2, 4, 6, 8. Because we just care about what things are in there, not their order. A sequence is... Let's call it a set with an order. Otherwise known as a list. So if I was going to put these numbers in a particular ordering, let's do 2, 4, 6, 8. That would be a sequence. And it's normal to name each term in the sequence with its own value. So A subscript 1 would just be the first term. A subscript 2 would be the second, and so on. And you could use letters other than A. You could say T or S or whatever you want. Okay, a series is just a sum. So, for example, if I wanted to make a series out of this sequence, I could just add them all together. Okay, so nothing mind-blowing so far. Let's say you are imagining a sequence. You're imagining a list of values. So there are 3 typical ways of showing what sequence you have in mind. The first is you could just list a couple terms. List the first 4 or 5 terms to show what pattern you have in mind. So let's write one. And do please go ahead and write this together with me. So 1, 2, 4, 8, 16 is maybe enough to show the pattern I have in mind. And I'll write ... to indicate an infinite sequence that just keeps going. Let's go ahead and label the terms. So that'll be the first term, the second term, the third term, the fourth term, and so on. Okay, so that's a typical way of doing it. If you really wanted to specify the pattern, you would actually have to give an infinite number of values. Because there's an infinite number of different equations that would fit these first 5 numbers. But in our class, it's going to be sufficient to give enough to show the pattern that you have in mind. Okay, let's talk about a recursive equation. So the word recur, the normal English language word recur, means something like to come back or to happen again. So a recursive definition is a definition where the terms recur, where the terms come back inside the definition itself. An example is going to make this extremely clear. So let's rewrite this sequence right here. So one more time. I'm gonna pause so that you can write it. So the idea of a recursive definition is you're going to explain how do you get from one term to the next term. If there's an easy rule that you can use of getting from one term to the next term, it's going to be easy to write a recursive definition. So ask yourself, how am I getting from each term to the next term? If you said you're multiplying by 2, that is the sequence I had in mind. But how do you write this idea down algebraically? So one thing you could say is, like if I'm at term 2 and I multiply by 2, now I've arrived at term 3. If I'm at term 3 and I multiply by 2, I've arrived at term 4. Notice that that's always true. Well, here, let's write one more. Term 3 times 2 equals term 4. The pattern is, if I want to know term n, that's what I want, how do you figure out the nth term? It's just the n minus 1 term times 2. So the term I want equals the previous term times 2. So there's term I want. This is the previous term times 2. So the important thing, though, is when you see an equation like this, you want to think, oh, this is just telling me how to find the next term based on previous terms. It's telling me how to advance in the sequence. This by itself is not enough, though. If all I had was this, here's the sequence that this much describes. All that equation says is how you get from one term to the next term. It's just saying each term is two times the previous. But it doesn't actually tell you anything about the numbers in there. So, for example, this equation matches the sequence 11, 22, 44, 88. Right? Because each term is 2 times the previous. But that's a totally different sequence than this sequence up here. They just have the same pattern for how you advance. So for recursive definition, you have to have two things. You have to have an equation that says how you get from a previous term to a next term. And then you also have to have a starting point. So you can say the first term equals 1. And so if you have both of those terms together, if you have both of those pieces of the definition together, now you really are specifying a unique sequence. So you've got a starting point, and this is how to get from one term to the next. Something that somebody pointed out in second block, which was a very astute observation, is this is not true all the time. For example, if n equals 1 here, if n equals 1 here, this is saying that the first term equals 2 times t subscript 0, so 2 times the 0th term, but there is no 0th term, and that doesn't make sense. So a really good observation is the first term is 1. This equation only applies for n larger than 1. So it's sort of like if we're talking about the first term, you use this. If we're talking about n is the term number, so if we're talking about any term after the first term, then we're going to use that equation. So you can kind of divide up which equation gets used. You can think about it piecewise. Okay, last little bit. So recursive equations are sometimes easy to write if there's a really clear rule for how you get from each term to the next term. The problem is they might not be that useful. They might not be that useful if you really want to know the actual term number. So if I wanted to know what was the 111th term, here's what the recursive rule says. The recursive rule says, oh, you want to know the 111th number? Here you go. It's just 2 times the 110th number. And then you might say, well, wait, what's the 110th number? And so you can use the recursive definition again. It says, you want to know the 110th number? Oh, it's just 2 times the 109th number. And you say, well, wait, what's the 209th number? And it says, oh, it's just 2 times the 108th number. But you have to go a long way before you eventually get down to what's the first number. What is T1? So the recursive definition doesn't immediately tell you a number. It just tells you what each term is if you already know the previous term. If you don't, maybe what you're really looking for, here let's annotate what's going on here. So recursive definition doesn't give you a number, at least not right away. So if you're looking for a number, what you really want is you want an equation for the nth term where you just plug in n and it will tell you what's the value at the nth term. So you want t subscript n equals, some equation. Very often this is called an explicit definition to contrast it with a recursive definition. A recursive definition says, here's how you find the nth term based on the previous one. An explicit one just says, here's how you find the nth term, full stop. Okay, so if you look at the same pattern here, why don't you look at it and decide, what do you think is the equation? Okay, you might have noticed it is 2 to the n minus 1. People in the other blocks saw this in several ways. One way you could see it is just by noticing, these are all powers of 2, but 2 to the 4th power doesn't make 8. It's actually 2 to the 3rd power. And this 2 to the 3rd power doesn't make 4, it's actually 2 squared. So it's sort of like you have to take the term number and subtract 1, and then that's the exponent you want that's going to give you the value. And so that's what we're saying here. We're saying take the term number, subtract 1, that's the exponent that gives us the value. So here, this is really nice, because here if we want to say what was I trying to figure out here, the 111th? So if we say what is the 111th term, the answer is 2 to the 110. Right away we know the answer. Whereas down here, you only know the answer if you already know the 210th term. All right, that's the end of the introduction. Hopefully nothing super weird. In the cards, you're going to have a chance to work with recursive definitions, explicit definitions. Flip the page over real fast. There are two very important kinds of sequence, arithmetic sequence and geometric sequence, but don't read it right now. You're going to discover all about them in the problem set. So only at the end of the problem set, when you do card 3 and card 4, are you going to come back and then do that backside. Card 3 and card 4 are a huge part of the learning, so some of the other blocks started to slow down a little bit at the end of card 2. They thought, we've done some great math. It's just like lay out a little bit. Don't slow down. Card 1 and card 2, awesome. Card 3 and card 4 are going to be really crucial because you're going to need to know these facts, deep in your heart for at least this unit and probably for a couple more units. Okay, good luck on the problem set.